Welcome back everyone. Today we learn about electromagnetic induction. Electromagnetic induction is caused by a change of magnetic field within a closed circuit, resulting in induced EMF or current within the closed circuit. In this chapter, we will also learn how an AC generator and a transformer works as well. Let us talk about magnetic flux. It quantifies the amount of magnetic field lines in a region. The amount of magnetic flux is dependent on magnetic field strength and area of the region. The SI unit of magnetic flux is the Weber. Magnetic flux linkage quantifies the total amount of magnetic flux that are present in numerous circular coils. The amount of magnetic flux is dependent on magnetic field strength, area of the region, and number of coils. It also uses the Weber. Magnetic flux is calculated as the magnetic field strength multiplied to the area of the coil. Hence, phi equal to B times A. In the calculation of magnetic flux, magnetic field lines need to be perpendicular to the area of the coil. There are two laws that we will learn for this chapter: Lenz's law and Faraday law. Firstly, Lenz's law. It states that the direction of the induced current is such that its magnetic effect always opposes the change producing it. What does that mean? Let us use an example. Take a look at this circuit. In this circuit, the magnet is being brought closer to the solenoid. This results in the needle to deflect to the left. Why? Well, the induced current is produced such that the solenoid becomes magnetized, and the point nearest to the magnet becomes the north pole to oppose the approaching magnet. Now, the magnet is moving away from the solenoid. What do you observe? The needle deflects to the right and not the left. Induced current is produced such that the solenoid becomes magnetized, and A becomes the south pole to oppose the magnet going away from the solenoid, since the south pole of the solenoid attracts the north pole of the magnet. Let us look at another example. Take a look at this circuit. When the switch is closed, a magnetic field is produced around the right solenoid. This causes the left solenoid to induce a current such that it opposes the change in magnetic effect by the right solenoid. Hence, the galvanometer needle deflects. After a short while, the magnetic field from the right solenoid remains unchanged. This causes the left solenoid to not induce a current as there is no further change in magnetic effect by the solenoid. Galvanometer needle goes back to zero. When we are encountering questions involving electromagnetic induction, we need to take note of the deflection of the needle, the change in magnetic effect by the source of magnetism, and the design of the solenoid to oppose the change in magnetism. Faraday's law of magnetic induction states that the strength of the induced EMF is proportional to the rate of change of magnetic flux linked with the circuit. Therefore, this can be described with the following formula as shown. We can deflect the needle even more. Increase the number of turns of the solenoid so that more coils can cut the magnetic field of the magnet. Increase the number of turns of the solenoid so that more coils can cut the magnetic field of the magnet. And to increase magnetic strength to increase the number of magnetic field lines. Let us touch on a question. Here we have a magnet and a solenoid. In this experiment, we will be dropping a magnet into the solenoid. After that, we receive the graph as shown. As you notice, you will observe that the jump as the magnet enters the coil is shorter and thicker than when the magnet leaves the coil. Explain why will the jump in EMF when the magnet leaves is thinner and larger in amplitude as compared to when the magnet enters the coil. As the magnet falls, the speed of the magnet's descent increases. Thus, the time for it to leave is shorter than the time for it to enter. Hence, the jump is thinner when the magnet leaves the coil. By Faraday's law, the induced EMF in the coil is directly proportional to the change in magnetic flux. The magnetic flux change as it descends is faster. Hence, the jump in induced EMF is larger in amplitude as it leaves the coil. Why is there no induced EMF in the coil when the magnet falls in the solenoid? By Faraday's law, the induced EMF in the coil is directly proportional to the rate of change in magnetic flux. Since there is no change in magnetic flux when the magnet descends into the solenoid, no induced EMF is produced. Draw on a graph of induced EMF against time for this scenario. The solenoid is replaced with a coil. Here is the new graph. With comparison to the previous graph, the amplitude reduces as the rate of change of magnetic flux decreases due to the number of coils cutting the magnetic fields being lesser. In addition, because the magnet enters and leaves in a very short time, the two jumps becomes even closer. Now, let us approach the topic of an AC generator. A generator produces electrical power from mechanical power. The induced current can either be an alternating current or a direct current. Alternating current is current that regularly changes its direction over time. In the previous topic, we have touched on the topic of DC motors. However, we will be learning about the AC generator. Although they look the same, they operate differently and have a few differences. Motors convert electrical energy to kinetic energy. Generators convert kinetic energy to electrical energy. There are subtle differences between the DC motor and the AC generator. Firstly, a generator uses slip rings instead of a commutator, which will be explained later. Another difference is that, because an AC generator operates by converting mechanical energy to electrical energy, it produces a current, and hence we would replace a battery with an electrical load like a bulb or a bell. Slip rings comprise two complete rings that allow the direction of induced current to reverse every half revolution in the coil. With the slip rings, an alternating current is obtained. In the previous chapter, we have learned about the Fleming left-hand rule. However, for this chapter, we will be using the Fleming right-hand rule. How do we know which hand to use? Well, we use the Fleming left-hand rule when we are using motors or any electronic device that converts current to produce a movement. However, we use the Fleming right-hand rule for electronic devices that converts movement to induce and produce a current, such as in generators. Using Fleming's right-hand rule for the left side, we observe that the magnetic field points to the right. The coil moves upward. This results in an induced current as shown. Meanwhile, for the right, the magnetic field still points to the right, the coil moves downwards. Hence, this results in the current moving in this direction. The graph shows the variation of the induced EMF over time. Let us discuss them individually. Now, we take a look at the side view of the coil. Let us focus on one side of the coil. At this point that we call point A, the current induced is at a maximum. This is because the force of the coil is exactly perpendicular to the magnetic field. Hence, the cutting of the magnetic field lines is at a maximum. At B, the induced current reduces since there is a decrease in perpendicular component of the magnetic field, By. As the coil rotates, By becomes smaller. With Faraday's law, from A to C, the rate of cutting magnetic field lines by the coil decreases as the force on the coil becomes parallel to the magnetic field. Induced EMF falls. At C, since the magnetic field is parallel to the applied force, and there is no cutting of magnetic field to generate an induced current. There are a few ways where the electromagnetic force of the generator can increase. Here is a table which shows some changes. We can use Faraday's law to understand how the changes impact the current in the coil induced. Let us discuss them one by one. Firstly, we can double the speed of rotation of the coil. As the coil cuts the magnetic field lines at double the speed, the amplitude of induced EMF doubles due to the increase in the rate of change of magnetic flux. However, in this case, the frequency of the induced EMF doubles as well as the number of cycles done over a unit time doubles. Hence, it would result in the following graph as shown. In addition, we can also double the number of turns in the coil. More coils will cut the magnetic field lines, suggesting that the change in magnetic flux will double. Hence, the amplitude of the induced EMF is as shown. Next, increase the magnetic field strength. This increases the number of magnetic fields from the magnet, resulting in more magnetic field lines being cut by the coil. Hence, the rate of change in magnetic flux increases, resulting in the graph being as shown. Lastly, we can add a soft iron core. Winding a coil on the soft iron core to concentrate the magnetic lines of force through the coil, allowing more magnetic field lines to be cut by the coil. Hence, the amplitude of the induced EMF increases as the rate of change in magnetic flux increases. Hence, it results in the following graph as shown. Now, let us touch on transformers. Here is a diagram of what a transformer looks like. You will notice that there is an AC supply connected to the transformer. A DC source will not work as it cannot create a changing magnetic field in the soft iron core. In a transformer, the primary coil will produce changing magnetic field. The iron core will concentrate the magnetic field lines to the secondary coil. Primary and secondary coil share the magnetic flux density. Hence, magnetic field induces a current in the secondary coil. There are a few ways to make a transformer ideal. Firstly, there should be no resistance in the coil. Next, no flux leakage from the iron core. In other words, all the magnetic field lines should not leak out of the transformer. Lastly, no power should be lost as heat in the transformer due to eddy currents. Eddy currents are produced when the magnetic field of the induced current opposes the existing magnetic field. The heat is generated due to the current in the conductor. Thus, energy from the transformer will be transformed into heat energy. In previous topics, we have learned that the efficiency can be calculated as useful output power over the input power. Recall that power can be written as a product of voltage and current. Hence, we can rewrite the equation as shown. In an ideal transformer, we can say that the efficiency will be 1. Hence, in an ideal transformer, we can say that VSIS equals VPIP. There are 3 ways to improve the efficiency of the transformer. Firstly, an effective soft magnetic material can be used as the core to concentrate the maximum magnetic field produced at the primary coil. Next, we can use low-resistance copper wires which reduce losing energy in the form of heat in the coils. Lastly, we use a laminated core to reduce the flow of eddy currents that cause additional heat loss in the transformer. Earlier on, recall this equation that can be used for the calculations in a transformer. Here are 2 different equations. These 2 equations can determine the type of transformer. Either a step-up or step-down transformer. In a step-up transformer, the turn ratio is more than 1. We can conclude that in the secondary coil, the EMF of the secondary coil increases, but the current of the secondary coil is reduced. The converse can be said with the step-down transformer, whereby the EMF of the secondary coil falls while the induced current in the secondary coil is enhanced. Here, we have a diagram to show how electricity is generated. A power plant emits electrical currents which will change once they pass through the step-up and step-down transformer. They will then be further transferred through the wires to power up homes, companies, and others. The cables used for transmission to various stations tend to be normally very thick. Thick cable has low resistance which thus limits power loss through heat. Thick cables are also more costly and more difficult to lay or incur a higher infrastructural cost. For less current to be flowing through the wire, a high output voltage is preferred in order that the current is kept low. Low current means lower power loss, which equals I squared R. Let me demonstrate it with a few examples. Here, we have the cable as shown. The resistance of the cable is 2 ohms and has a lower power output of 2000 watts. Let us adjust the voltage to 2000 volts to give us 1 ampere of current. This will result in the power loss by the cables to be 2 watts as shown. Alright, what if we reduce the voltage to 200 volt? This increases the current to 10 ampere. Hence, we will use the power loss equation to give us 200 watts. That is so much more power loss compared to the previous one. Hence, a high voltage reduces heat loss. A step-up transformer is used when transmitting the current out of the power station. Power output is constant and this is translated to Vs and Is, and when Vs is kept high, Is becomes low.
That's all for today. Thank you for the effort to learn with me. Stay tuned for more interesting lessons. See you next time. Bye-bye.